Okay, so let's talk about standard enthalpy of formations and how we can use those to calculate the enthalpy of reactions. Okay, so one of the objectives is going to be to define and apply the terms standard state and standard enthalpy of change. That's what that little circle means, is standard. And then to determine the enthalpy change of a reaction using standard enthalpy changes of formation. So we've looked at several different ways so far to calculate the enthalpy of a reaction, delta H. We can do it experimentally with calorimetry. That's the Q and relating Q of solution to Q of the reaction. And then we looked at Hess's law. Last screencast looked at average bond enthalpies, and now we're going to look at standard enthalpy of formation for reactants and products. So what is the standard enthalpy of formation? Well, the definition is it is the enthalpy change that occurs when 1 mole of a substance is formed from its elements in their standard states. That means at 25 degrees Celsius and 1.00 times 10 to the 5th kilopascals. And then enthalpies of formation are provided in table 11 of the IB booklet. What do they look like, you may ask yourself? Well, let's take a look at this booklet. Those are the bond enthalpies that we've just used. Here is delta HF, and this is what they look like. Don't worry about these other two columns. We'll get to those later. All right, so substances, and these are mainly organics. So you're either going to have to look up the formula or look up the name, the state, and the enthalpy of formation. Okay. So that's what we'll be using. Okay, so enthalpy of formation, that delta HF, is defined as the enthalpy change for the reaction in which a compound is made from its constituent elements in their elemental forms. Okay. Let's look at some standard enthalpies of formation measured under standard conditions. Okay. If you notice something, these are all compounds. These are not any elements. The standard enthalpy of formation for an element, delta HF for elements in their standard states, is 0. Carbon in its graphite form is considered a standard for carbon. So its delta H in C graphite is 0. O2, H2 gas, bromine liquid, iodine solid, all of those would be 0 standard enthalpies of formation. So how do we use these? Well, let's take a look at the combustion of propane. Propane is C3H8. In its combustion, we would react it with oxygen, forming CO2 and H2O liquid. Let's apply Hess's law and look at this reaction as occurring in 3 steps. Okay. The overall reaction, here I have my products. Those are my reactants, and here I have my products. So this is actually the delta H of the reaction that we're looking for. We're going to take the long way to get there. First, we're going to take this propane and oxygen, okay, and have it be graphite, H2, and O2. Okay. And there's a change in enthalpy associated with that. The next step is going to be taking those, the graphite and the O2, and forming CO2 from it. Okay. The third step is going to be taking that H2 and the O2 and forming water. So what we've done in the first step is taken everything and gone to its elements. Then from those elements we form at first one product that's a compound, and then we form the other product that's a compound. If you notice, these 3 changes, if we take them overall, get us back to that first overall delta H that we were looking for. And that is Hess's law that we have applied. So that's our overall equation. Now, how can we use the enthalpy of formation for those different compounds to come up with an overall delta H of reaction? We're going to do it in this way. Delta H of the reaction. Okay, we probably should say it's going to be at standard conditions because we're using the delta H of formation at standard conditions. Okay, so delta H of the reaction is going to be equal to the sum of the number of moles times the delta HF standard of products minus the sum of the number of moles delta H formation of the reactants. N and M are the stoichiometric coefficients, meaning the coefficients in the balanced chemical equation that I'm using. So if we look up the values in that heat of formation table, we have delta H is equal to 3 times delta H of CO2 plus 4 times delta F of water. And I did mean to say enthalpy of formation for CO2, enthalpy of formation for water, minus the enthalpy of formation for propane, and minus the enthalpy of formation from O2. Since O2 is an element, its heat of formation, delta H of formation, is 0. Add those up, and we come up with an overall heat of reaction, change in enthalpy for that reaction. Okay. So let's just do a couple of examples to finish out this section. We're going to write the balanced equations for the formation of 1 mole of the following compounds from their elements in their standard states and include delta H 0 of formation. Pause the screencast and try to do this yourself, and then we'll look at the answers. Things to note. Silver solid, chlorine is a gas, making 1 mole of the substance. You want to be 1 mole, so you're going to have weird coefficients sometimes in here so that I make 1 mole of the substance. This delta H of formation came from my table for silver chloride. The next one, calcium is a solid. Remember, carbon is graphite, 3/2 of oxygen is a gas. The heat of formation for calcium carbonate from the values. These are how you would write formation equations. Then again, using the elements in their standard state to make the compound, pulling the delta H of formation from that table. Okay. So for each of the following reactions at 25 degrees Celsius, would the enthalpy change represent a standard enthalpy of formation for these three examples? For each that does not, what changes are needed to make an equation whose delta H is an enthalpy of formation? Pause the screencast and please answer. Okay. Looking at these three equations, we can see the first one uses sodium as a solid, and that is what sodium would be as an element. Oxygen is a gas, and then Na2S as a solid. So this looks like it is an enthalpy of formation because the reactants are in their states as they would be as elements. Looking at the second one, I have 2 potassiums as a liquid and chlorine as a gas. That's good. Making 2 moles of potassium chloride solid. We really want this to be a 1. Potassium as an element is going to be a solid. And then 1/2 of a chlorine molecule as a gas. and this is going to make KCl as a solid. That would represent the equation for the enthalpy of formation for potassium chloride. Looking at this third one, it should be flipped around. 2, carbon should be graphite. So we're going to change this to 6C graphite plus 6 H2's, hydrogen gases, plus 3 oxygens, gas, go to make C6H12O6 in its solid state. That should be good. Yes. Okay.